Hello, my name is Nicole Martin, and this is my video for physics extra credit, and I'm in lab section M05. So the lecture I attended for extra credit was given by Alan Nathan, and it was titled Baseball and Physics. You can learn a lot by watching. And basically, the topic of the entire lecture was the breakdown of the ball-bat collision during baseball games. So he started off introducing like what actually happens during the ball bat collision. So first, when the ball is hit by the batter, it deforms, and that results in a loss of the ball's energy. And the bat transfers energy to the ball, which changes the ball's momentum. The ball leaves with about half as much kinetic energy as it comes in with, and the ball slows down after coming in and the bat slows down after coming in contact with the ball. And so the next section in blue is about connecting what Mr. Allen was talking about to concepts that we've learned in our physics class. And so the interaction that happens between the ball and the bat is a collision, and as we know, a collision is defined as like there's two objects interacting, and there's little interaction before contact, but when they do come in contact, there's a large force between the objects, and they're in contact for a very small time. And from the introduction, we can see that the ball-bat collision is an elastic collision because the final kinetic energy of the ball is not equal to the initial kinetic energy of the ball. So then he went into the dynamics of the ball-bat collision, and this section of the lecture was about what determines the batted ball speed. So basically how fast the ball is going after it's hit. So some key factors that determine BBS is the pitch speed, how fast the pitcher throws the ball, the bat speed, which is how fast the guy holding the bat is going to swing the bat, the weight of the bat, because that deals with the moment of inertia, and the collision efficiency, which is a property of both the ball and the bat. So he gave an equation, and that part of the lecture was more like in-depth research, which kind of goes beyond the scope of this course, but here I have it listed. And we see that some key factors have to do with the velocity of the pitch and the velocity of the bat, as well as a coefficient of restitution, which is denoted as Q. And so Mr. Allen stated that the velocity of the bat matters much more than the velocity of the pitch. And we'll see why that comes into play later in the video. And basically, the coefficient of restitution is the bounciness of the ball. So if you hit the ball at the right spot, you contribute to how far it'll bounce off the bat, which is really important in baseball. And so here we have the weight of the bat, moment of inertia, in orange, because the next section is an example of how the moment of inertia and the weight of the bat has to deal with the batted ball speed. And so these are basically examples of the relation between the weight of the bat and the batted ball speed. So one example is corking, which is basically filling a portion of the bat with a lightweight material. And so the lighter weight allows you to swing the bat faster, which allows for you to come in good contact with the ball, but it has a lower collision efficiency, so the ball won't travel as far. Also, he went into talking about aluminum versus wood bats, and aluminum bats have a higher bat speed because they're hollow, and that means their moment of inertia is lower, and that's also known as the trampoline effect. However, wooden bats have a higher collision efficiency, so the ball will travel higher when it hits a wooden bat. And so finally, I just wanted to discuss something that I found interesting from the lecture, and that was that he stated that nothing on the handle end of the bat contributes to the ball's rebound speed. So basically, that means like the most important part is like the larger, fatter end of the baseball bat hitting the ball. And so this is because like when the batter swings the bat, by the time the handle begins to move, the collision between the ball and the bat is already over. And so like as you can see in this graph that was like taken from one of Mr. Nathan's research reports, where the arrow is pointing, that's signifying when the collision happens. And so after this point, that's when the rest of the bat starts to move. So at this point, like the collision is complete and the handle end hasn't even started to move. And so an example he used for this was Todd Frazier's no hands home run, which is shown here. As you can see, like he literally throws the bat at the ball, and the ball was hit in the right spot, the right end of the fat end of the bat, and he got a home run. And so I thought that was really interesting for the lecture, and that's my video.